Math 230, Cuesta College. I'm Joe Vasta, and this is the review for exam 3. I call it review 3. I'm going to do some review exercises from the book from chapter 4 and chapter 5. If you haven't tried them, then you might want to stop the video and work the problems out on your own. So here we go. Chapter 4 review looks like this. The first thing we covered happens to be the hieroglyphics, and there they are. I know these look a little small here. So you don't have to memorize what these things are, but what we have is a question that says write the Egyptian number in our system. So what we have, 2 ones, so in the ones place I put a 2. 3 horseshoes or heels, that's going to be 30. So if we just had those 2 things, we would have 32. Then we have 1, 2, 3, 4, 5 scrolls. A scroll is 100, so this is 500. 532 is that right there. We have a bent finger. So if you go on automatic pilot, you might just think you should put a 1 there. But the bent finger is a 10,000. There are no flowers. Since there are no flowers, we put a 0 there. And the bent finger, which is in the 10,000s place, there's only 1 of them. And then we have 1, 2, 3, 4 tadpoles. So we are going to put a 4 there. There are 400,000. So my answer happens to be 410,532. And so those problems are pretty straightforward. And then we have one that says write the number in Egyptian hieroglyphics. So I'm going to start off with the 4. I have 4 ones. Okay. I have 0 10, so I'm not going to put any heel bones. Like the last one had some heel bones, this one does not have any. Then I have 3 scrolls. So 1, 2, 3. And then 2,000. So 2 of these lotus flowers. And I make mine a little bit different from the flower in there. And so I better make another one here. So there's our answer right there. There's our hieroglyphics. We have just covered the first section. Okay, our next problems happen to be these ones right here. Roman numerals. Okay, the first thing about Roman numerals is that we should probably write down what they are. I, V, X, L, C, D, M. So the I is a 1, the V is a 5, the X is a 10, the L is a 50, the C is 100, the D is 500, the M is 1,000. So why don't we go ahead and write out these things in hieroglyphics. Before we do that, I'm going to go ahead and put a puzzle up. We did not do a puzzle, so I'm going to stop this video, get a puzzle, and then come back to this. Let's take a look at the puzzle. Which word does not belong? And so what we have 11 words here. You have to figure out which word does not belong. That's the puzzle for this review. Let's get back to our problems. Roman numerals. Write each Roman number in our system. So what we want to do is see if there are any increases. We have M, that's 1,000, 1,000. C, 100, D. Right there is an increase, CD. And then we have, so that's 500 down to 10, up to 50, so we have another increase right here. and then down to 1 and up to 5, so 3 increases. The CD happens to be 400. XL is 40. IV is 4. So what is this number? This number is 2 M's, so 2,444. So make sure you know how to do stuff like this for the exam. This Roman numeral has a bar over some of the letters. That bar multiplies by 1,000. So I'm going to break this up into 2 problems. I'm going to first do CIX. Well, CIX, C is 100, IX, that happens to be 9. Your increases involve 4s and 9s. So this is 109. That's that first part. Now, of course, because there's a bar over it, we multiplied that number by 1,000. So I put a comma there. And now I'm going to analyze this part and put that number right there for those next 3 digits. CM, 100, 1,000, down to 50, and then we have 10, 10, 5, 1, 1, 1. So there's only one other increase, it's right there. CM is 900. So I have 109,000. This is going to give me 900 LXX, that's 70, VIII, so 5, 6, 7, 8. We have that right there. So the subtraction rule for Roman numerals, it gives you the 4s and the 9s. So we'll need to know that when we're doing it this way. Okay, so write each number in Roman numerals. And so what I'll do is I'll just circle my 4s and 9s in orange. And that's where I have to do the subtraction principle. The other thing to remember is go 1 digit at a time. So this one tells me 2,489. I need 2 thousandths. So MM. Now I go to the 4. What does that represent? 400, and I'm going to have to do some subtraction. 500 minus 100 is 400. So this is going to give me, what is it going to give me? It's going to give me CD. Now the 8 is 80. We have to get 80 without subtracting. So that's going to probably be 50, 60, 70, 80. So L, X, X, X. And then the last one is a 9, which is gotten by subtracting. It's going to be IX. So the way you would say 2,489 with Roman numerals is like this. Okay, the next problem. 297,826. Because this number is greater than or equal to 4,000, we must use bar notation. So what I'm going to do is just split this into 2 problems. 297 is my first problem. 200 CC. 90, this is the subtraction rule, 100 minus 10, so that's CX, it's going to be XC. And then we have 7, which would be a 5, 6, 7, so VII. We put a bar over that because that multiplies it by 1,000. And so this is the 297. With a bar, it's 297,000. Okay, so now we're going to move on to the 826. There's no 4s or 9s, so this is just putting some symbols together. 800 would be 500 D and CCC. 600, 700, 800. So with the Roman numerals, you shouldn't see more than 3 of the same symbols in a row. We don't want to write 800 as C, 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 C. We want to write it as D, C, C, C. The 2 represents 20, so 20 is X, X, and the 6 is VI. So there it is. I've just taken one of our numbers right here, expressed it with Roman numerals. Let's move on to the next section, changing base. That's what we're going to do right here. Change 402, which is base 5, to base 10. So I always remember that it's easier coming back home to your home planet base 10. And so this was going to actually be pretty straightforward. Hopefully you've seen those lectures. I'm coming from base 5, so this number 402, it has the 1's place, the 5's place, and then we multiply by 5 again, so this is the 25 place. And below those numbers, I'm going to put 402. And then I multiply 4 times 25. I'll write it out this time. 4 times 25 plus 0 times 5 plus 2 times 1. So this is 100 plus 0 plus 2. So that's going to give us 102. That's a base 10 number. We don't need parentheses with a little 10 because this is our number system, base 10. Well, let's try this one right here. Change this base 2 number to base 10. Now base 2 has another name. It's binary, but they didn't say binary here, so let's go ahead and do the same procedure that we did above, except this is base 2. So I have 1's, 2's, and we multiply by 2 each time. 4 times 2 is 8, times 2 is 16. How many do we need? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So the sixth one would be 32. And so right below those numbers, I put the 0's and 1's. So this is 1, 1, 0, 1, 1, 0. So I have 1 times 32, which is a 32, plus 1 times 16, plus 0 times 8, plus 1 times 4, plus 1 times 2, plus 0 times 1. So let's go ahead and add this up. Probably would have been better for me because I'm doing all this without a calculator. To do it this way. 10, 14, carry the 1. Then we have 3, 4, 5. So it looks like my final answer is 54. Let's go ahead and do another problem. Problem number 9. Change something to base 10. We're still doing that. Change 3C, which is base 16, to base 10. So 3C, I'm in base 16, I'm going to base 10 just like the last two problems. So I'm going to go ahead and write out some powers of 16. I'm going to always start with a 1. And then I multiply by 16 and get a 16. Now if I had to keep going, I would multiply 16 times 16 and put the next thing there. But there's only 2 symbols there. So right underneath I'm going to put a 3 and a C. Now here's the deal. It may be hard for us to think about what is C times 1. Well, we have to go beyond that. This base 16, which is also called hexadecimal, uses 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So those are 10 symbols, but it actually uses 16 symbols, different symbols. So 10 would be an A. 11 would be a B, C, D, E, F. So that's what base 16 is. So this is 12, 13, 14, 15. So this C, we know what it is. It's really a 12. So this gives us 12 times 1. So 3 times 16 is 48 plus 12. You can line that up if you want, but when you finish adding that up, you will end up getting 60 for your answer. So expect to see base 16 on the test, which is also called hexadecimal. Problem number 10. Now, how is problem number 10 different from the last 3 problems? The last 3 problems, we were changing to base 10, which was cool. But now, the next few problems, we are going from base 10, see there's no parentheses, to a different weird base. And it's always a little more difficult leaving home, going to a strange place, and that's what we're going to do. This is the one where there were 2 methods. There was the shopping method and the long division method. I'm going to go ahead and do the long division method first. I will then do the shopping method over here, and then in the future I'll just do one method. We don't have to see 2 methods every time. If you want to see me do that, go back and look at the other video on this that we did earlier. So changing 35 to base 2, I put 35 kind of low here because I'm going to be doing lots of long divisions on it. 2 goes into 35. Well, that's going to be 17 times. 17 times 2 is 34, so this gives me a remainder of 1. 2 goes into 17. Well, that's going to be 8 times. 8 times 2 is 16, so I'm going to get a remainder of 1. 2 goes into 8. 4 times perfectly, but we still have to put the remainder 0. 2 goes into 4, 2 times with a remainder of 0. And 2 goes into 2, 1 time with a remainder of 0. And then we go down the river here. So our final answer, this is a base 2 number I'm going to write, is 1, 0, 0, 0, 1, 1. And to tell the world that we are using base 2, we put parentheses around it and put a 2 there. The other method that we learned that some of you might like better will give the same result. This was the shopping method. The shopping method, you had $35, you had a 1 bin, 2 bin, 4 bin. Okay, so I'm just doing the base 4 thing, and then the next one would be 8, doubling each time, 16, 32. The next one would be 64, but I wouldn't be able to afford that. So now I put things in the shopping carts as I get them, and I always want to buy the most expensive one. So I'm going to buy a 32. So I subtract that. And I have $3 left. So I cannot get another 32, I cannot get a 16, I cannot get an 8 or a 4. I could buy a 2. And now I have $1 left. I'm going to use all my money on this, so I'm going to get one of those. So notice what we have here. We have, and that Roman numeral 1 is there. So I don't know what to do about that. What I have is I have 1 there, and then there's nothing in those carts, so I'm just going to put zeros there. And then look, 1, 1, which is exactly what you get from long division. So both methods are legitimate. Use the method you feel more comfortable with. Let's go ahead and do another problem. Change 528 to base 5. Okay, so I'm going to go ahead and do some long division on this. 5 goes into 528. So 5 goes into itself one time. 1 times 5 is 5. Subtract, I get a 0. Bring down the 2. 5 goes into 2 0 times. 0 times 5 is 0. Subtract, we still have a 2. 5 goes into 28. 5 times 5 is 25. Subtract, we get a 3. That is our remainder. Almost went off the paper there. Now I'm going to go ahead and put 5 into 105. Now, if you need to go off to the side to do that, there's nothing wrong with that. So 5 goes into 105. 5 goes into 1. No, it doesn't. 5 goes into 10. 2 times 5 is 10. Subtract, we get a 0. Bring down the 5. 5 goes into itself. 1 times 5 is 5. Subtract, we get a 0. So what we've learned from this over here, I'll put it in a little cloud. That's kind of a sad looking cloud, is that we end up getting 21 for the quotient, and we have to put our remainder of 0. Now how many times does 5 go into 21? 5 goes into 21 4 times 5 is 20, so you're going to get a remainder of 1. This number up here is less than 5, so we're done with this madness. Did I push it a little too far down near the bottom of the paper? Yeah. Is that embarrassing? Yeah. Am I going to have to live with this because it's on YouTube? Absolutely. But oh well, here it goes. My final answer is 4103, and that is a base 5 number, and that's method 2. And you know what, I wasn't going to do this, but I'll go ahead and do the shopping method because I want to just illustrate it one more time. So the shopping method says we're going to set up some baskets. The first one's always going to be the 1 basket, and then the 5 basket, and then we multiply by 5, so 25 basket. And then what is 25 times 5? Well, that would be 125. And then the next one up would be like 600 and something, 625, which we would not be able to afford. So I have $528. So I think I can buy like 125. 125. So this is a 3, a 0, and a 4. So I'll put 1 in the cart. Looks like I can buy another one. 125. So I have to borrow from the 40. So I look at this as a 40, so I'll write this as 39. And then there's a 13. 13 minus 5 is 8. And then I have 9 minus 2 is 7. And then I have $278. Now, some of you might have thought ahead and said, oh, well, we could have bought a few of them and you could have figured that out by doing some division in your head or on the paper. But I could actually buy 2 more of these because 2 more of these cost $250. And I can do that. $250. I know I'm a big spender. I don't know what I'm buying, by the way, but I just bought 2 more of these, and so I have $28 left. Let's put 2 more into the cart. So $28, I'm absolutely going to buy a 25. So I think people like method 1 better because, you know, for some of you this is funner. You're like, wow, this is cool. I've got money and I'm spending it all. I have $3. I cannot get a 5, but I can get 3 of these cheap dollar store items. And so now I have $0 left. And notice, look at this, there's 4 items in that cart. 1 there, 0 there, 3 there. This gives me the answer that I got using long division. So let's go ahead and do another one. We have to do another one because you should know how to do the ones that involve base 16. I'm just going to do long division on this problem. So I'm just going to use the method 2 that we learned. 203, and I'm going to put 16 into that. 16 does not go into 2, but 16 goes into 20. 1 times 16 is 16. We subtract, we get a 4. Bring down the 3, 16 goes into 43. How many times does it go into 43? I'm going to try 2 times. 2 times 16 is 32. I'm going to subtract, I get an 11, which is good. It should be less than 16. So that is my remainder 11. I cannot put 16 into 12. 12 is less than 16, so I'm done. I go down the river. So you might say, oh, here's my answer, 1211. No, 1211 is not the answer. So you might go, oh, it's 12 comma 11. Well, 12 comma 11 is not the answer as well. What do we have to do on this? Remember what we did here with the hexadecimal. I know it's at an angle, but the tripod is in the way. 12 is a C, and 11 is a B. So my final answer is not 12 comma 11, it's CB base 16. Now, there are times when you have a number that you change to base 16 that has like remainders and the top quotient where they're like 0 through 9, and then you wouldn't have letters, but there are some that have the letters. So make sure you know how to do these problems. Let's go ahead and do our last change of base problem, which is problem number 13. And anytime in this video, if you are feeling guilty because you didn't do the review, you can pause and see if you can do these problems on your own. Change 42e base 16 to base 5. So this is different than any of the other problems that we got on this review because there's no base 10 in here. So I'm going to give you the same drawing that I gave you before in lecture. Here's base 16 planet, base 16, and you have a number that says 42e. You want to go to base 5 planet, so you want to just go there. But the best way to do a problem like this is come to Earth first, and Earth is base 10. So we want to go like this, and then we want to go like that. So coming back home is always a little easier. I'm coming from base 16. This is where you go 1, 16, and then 16 times 16. I'll go ahead and compute that. 36, 6, 7, 8, 9, and then 1 times 6, and 1 times 1. So we have 6, 9 plus 6 is 15, carry the 1, 256. So this is 256. Below these numbers, I write 42e. 42e. Now what am I going to do with that e? Well, remember from our diagram there, if you can kind of read it sideways, e is 14. So this is 14. So we have to do 4 times 256. So I'll just go ahead and say multiply by 4. So this is 24. 20 plus 2 is 22. 8, 9, 10. So this is going to be 1024 for that one right there. Then I'm going to go 2 times 16, which is 32, and 14 times 1. And I'm going to add those together. The numbers are a little big, so we have 8, 9, 10, carry the 1, 3, 4, 5, 6, 7, a 0, and a 1. So it looks as if my base 10 number is 1070. So what I'm going to do is I'm going to go ahead and write up the 1070. It is not my final answer. You will get something like this on the test, and I guarantee there will be a few people who put that for their final answer because they forget, oh yeah, I've got to go to planet 5. And some people are like, ah, that was enough trauma for one problem. Let's just go on to the next one and box this one. So don't be one of those people. We want to now change this to base 5. I'm going to go ahead and do the long division method. I put the 10, 70 right there, and I put 5 into it. 5 goes into 1, no. 5 goes into 10, yes. 2 times 5 is 10. Subtract, we get a 0, bring down the 7. 5 goes into 7. 1 times 5 is 5. Subtract, we get 2, bring down the 0. 5 goes into 20. 4 times 5 is 20. Subtract, we get a 0. We must put the 0 there for our remainder. Now I've got to put 5 into this number. Now this is a little big, so I'll take it off to the side. 5 goes into 2. No, 5 goes into 21. 4 times 5 is 20. Subtract, we get a 1, bring down the 4. 5 goes into 14. 2 times 5 is 10. Subtract, we get a 4. 4 is our remainder. We write 42. That's this guy here, the quotient. Remainder 4. Now, what we're going to do is we're going to put 5 into 42. How many times does 5 go into 42? 8 times. We know 8 times 5 is 40. We have a remainder of 2. 5 goes into 8. 1 time with a remainder of 3. Go down the river, and that is the base 5 number, which is 13240. And that is our answer. So let's go ahead and put our answer like right here. 13240. Base 5. And we're careful not to say 13,240 because right when we say 13,000, we're talking base 10, and this is a base 5 number. This is the most traumatic one because it involves both methods, changing to base 10, which is this method, and changing from base 10 to a weird base, which is this method, or you could have done the shopping method. This gives us problem number 13. We're going to move on to ASCII. Problem number 14. Translate the following binary code to English. So look what we have. We have a bunch of zeros and ones here, but they're grouped together in 8s. 8 bits. Bits are zeros and ones. 8 bits makes a byte. So I have, this is going to represent one letter, another letter, and another letter, and hopefully it will be a nice word. So what we want to do is we want to change each of these binary numbers, there's 3 of them, to base 10. To do that, we need to write 1, 2, 4, 8, 16, 32, 64, and I think there's 8 of them, so then we'd go 128. And below this, I'm going to go ahead and put the first one. So this is 0, 1, 0, 0, 3 ones, and a 0. The next one is 0, 1, 1, 0, 4 ones. And then this last number here is a 0, 3 ones, a 0, and 3 ones. So let's look at the first one right here. I'm going to actually do this in a vertical fashion. So what am I going to do? I'm going to go ahead and say there is 164 and an 8, a 4, and a 2. I'm going to add those together. See, what the zeros are, see there was 0 1s and 0 16s and 0 32. So what I'm concentrating on right now, I'll use a yellow sticky note here, is I'm concentrating on this number right here. I couldn't cover the whole thing up. Actually, I can. Watch this. So I'll put one right here. And look at that. High tech. This is so high tech. Okay. So that's where I'm getting the 64 and the 8 and the 4 and the 2. So let's go ahead and see if we have 8 plus 2 is 10, and then we have 18, carry the 1. And then 6 plus 1 is 7. So I have 78. This first one equals 78. Okay, now the next one. The next one is this guy right here. Okay, so I have 164, 132, 0 16, so I'm not going to write that, an 8, a 4, a 2, a 1. 8, 4, 2, 1. I'm going to add those together, and so I end up getting, let's see, that's 10, 21, 6, 7, 8, 9, 10, 11. So this is 111. Maybe I should have used these. 111 is our second number. And our third number, we're going to do the same thing. We're going to go 164, 132, 116. We do not have any 8s. 0 times 8 is 0. And then we have a 4, a 2, and a 1. 4, 2, 1. So let's add those together. We have 10, 14, 15, 16, 17, 18, 19, 6, 7, 8, 9, 10, 11. So this one gives me 119. Now we go over here. Capital A is a 65. I've got to get all the way to 78 because these guys right here, 111, 119, are going to be lowercase letters. 78. So let's see if we can do that. 66, 67, 68, 69, 70, 71, 2, 3, 4, 5, 6, 7, 8. So what do we have? A, B, C, D, E, F, G, H, I, J, K, L, M, N. Okay, so our first number here represents a capital N. You want to make sure that you make your N capital, do not make it lowercase. And I know I sound like a hypocrite saying that because if you've looked at some of my printing on my notes, sometimes I'll write capital letters where lowercase letters go, but never on a problem like this. So you can go back and look at the problems I've done. I was always careful. So now I want to count up to 119. So this is 98, 99, 100. 1, 2, 103, 4, 5, 6, 7, 8, 9, 10, whew, okay, 11, 112, oh that one's one of ours, 113, 114, 115, 116, 117, 118, 119. Okay, so A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W. I would actually take the lazy way out on this one and not write everything up, but I see my next question involves ASCII again, so I might as well have some things written out here. So looks like when I finish this up here, the 111 is an O, lowercase o, and the 119 is a W. So this word here is now where the first letter is capitalized and then those guys are lowercase. So there's the answer. Okay, and it's all base 2 here that we're talking about. Now look at this. Translate the following English word to ASCII. Leave your answer in base 10. So a W, that's a lowercase w, that's 119. Lowercase I, so we did all the work right here. Lowercase I is 105. And lowercase n is a 110. So there's the answer. Okay. So don't change those to base 2 if they ask you to leave them in base 10. So this completes the ASCII part. Let's move on to our next problem, if I can find it here. Here it is. So there it is. Write the zip code as a number. The check digit is included. Okay, so what are we supposed to do here? The first thing we want to realize is that this is postnet code, and the first and last bar are your guardrails. And so you really don't want to start using those as part of this code. They just go there. So I'm going to circle these in groups of 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. And then that one right there. So basically, this should be a pretty simple problem. You don't have to memorize these, but we did see they came from binary. Okay, zeros and ones, we derived this. So what we have here is you just have to look on the chart. What is short, short, tall, tall, short? Well, that's a 3. And then we have short, short, tall, that's a 2. That's that guy right there. And then this is tall, short, short, tall, short. Tall, short, short, tall, short, so that's an 8. And that one's the same thing. Tall, short, short, tall, short. That's an 8. And then this is tall, short, 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 tall, which is a 7. And the last one is short, short, tall, short, tall. That looks like a 2. I smeared that there. So there's your answer. It says the check digit is included, which means that's your check digit. That's number 2. If you add these up, they will add up to a multiple of 10. You don't have to check that, but I'm going to check this now. So that's like 27, 29. So that adds up to 30. So that's good that they really made that a legitimate check digit. Okay, number 17 says write the zip code in barcode. The check digit is included. So the check digit on this one is 0, and you probably can see they add up to 20. And this right here is just, this is going to be annoying because you have to start off with a guardrail. And then you just have to say, what's the 9? It is long, short, short. So that's the 9. I'll put a check mark there. 2 is short, short, long, short, long. 0 is 2 longs and 3 shorts. 1 is 3 shorts and 2 longs. 8 is long, short, short, long, short. And then 0, we had already done that right here. So this is a long, long, short, short, short. Don't forget your guardrail that goes on the other side. And there's postnet code. It's probably one of the more annoying problems here. Now let's deal with the check digit. We should know how to do a check digit. We're not going to do the check digit on barcodes. I showed you that just for fun. But we are going to ask you a question like this. Write the check digit that should be appended to the following zip code. 10020. So the first thing you do is you add up those digits. So this is 1 plus 0 plus 0 plus 2 plus 0. So this gives me 3. And we say, what is our next multiple of 10 after 3? Well, it happens to be 10. Multiples of 10 are 10, 20, 30, 40. So the next one is 10. And what do you need to get up to 10 if you were adding another digit on there? You would need a 7. So there's the answer. We used a whole piece of paper for this. Wow. Okay, well, there's probably a good reason I did that, because the next few problems that I do, I think there's like 4 problems, will come from Chapter 5, which was the graph theory. Chapter 5. Determine if the graph is traversable. If so, show how. An Euler circuit. If so, show how. So what you want to do in each of these graphs is you want to label the vertices. you count your odd vertices. So if there are 0 or 2 odd vertices, then it's traversable. If there are just 0 odd vertices, then it's an Euler circuit. Okay, so let's go ahead and count this. This vertex here has 2 edges coming out of it, so I put a 2 there. This one has 3. So we know right away that it's not going to be an Euler circuit because there's an odd vertex. So we have 2 coming out of there. 3 goes right here. 1, 2, 3, 4, 5. And then what else do we have? We have 1, 2, 3 for this one. 1, 2, 3. And 1, 2, 3. We have 1, 2, 3, 4, 5. So we have 6 odd vertices. 6 odd vertices. So is it traversable? I'm just going to say no and yes on these. So no, it is not traversable. And no, it's not an Euler circuit. It has 6 odd vertices, which does not fit that. Let's go ahead and do the next one. I'm going to label this vertex with 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Everything's 4 on this one. 1, 2, 3, 4. So we have 0 odd vertices, which means it's an Euler circuit. It's also traversable. So is it traversable? Yes. Is it an Euler circuit? Yes. So this one's a yes, yes. Now to tell you the truth, on your test I'm not going to have you show how. Why? Because I think I did that one time and it took me forever to grade. It was very confusing where people started. But if I was going to show you how, so this is what I would get if I asked people to show me how. You would start anywhere and there I did it. Now, of course, if you look back at the PDF, you won't know exactly what I did. So I think the first time I taught this topic in this class, I said, show how on the test. And I got pictures that look like this. I showed you how, I went ahead and drew it, and it's hard to say whether a person did that without lifting the pen off the paper. So on the exam, I'm just going to ask for yeses and nos on traversable Euler circuit. Just so you know, so you're not emailing me saying, hey, how come you didn't ask us to show how? Well, I'm not going to. Okay, bridge problems. The following diagram consists of islands and bridges. Is it possible to take a walk that starts at one island, crosses each bridge exactly once, and ends at the starting point? If not, what is the minimum number of bridges you must build to make it possible? Okay, so let's take a look at this. These islands are like big vertices, and the bridges are edges. So this vertex gets a label of 3. This vertex here gets a label of 1, 2, 3, 4, 5. 3 here, because there's 3 bridges touching that one, and then 1, 2, 3, 4, 5. Basically, what are they asking on this question? They are asking if this graph is an Euler circuit. That's really what they're asking, because they say it ends at the starting point. Ends at the starting point. An Euler circuit has to have 0 odd vertices. So what are we going to say for this? We are going to say no. It is not possible to take a walk that starts at one island, crosses each bridge exactly once, and ends at the starting point. If not, which that's what we have, what is the minimum number of bridges you must build to make it possible? Well, I gotta say that if I put a bridge here, those would become even. And then I put a bridge right there, those would become even, and then it would be all even numbers on the island. So the minimum number of bridges to build to make this possible is 2. You couldn't just do it with one bridge. Let's go ahead and do our last problem, the door problems. For each diagram, determine if you can pass through all the rooms while going through each door only once. If so, show how. So, each room is a vertex, and I will actually draw out the graph for you on this one. Each door is going to be represented by an edge. So I think I got all the internal doors. What I want to do is take care of these external doors. I have to put a vertex out there. So watch this. Okay, let's go ahead and label the vertices. Basically, what are they asking on this? If you can pass through all the rooms while going through each door only once. So you're just supposed to go on each edge one time. It doesn't say you have to start where you end, so they're really asking on these door problems, is the graph traversable? Let's label the vertices. 2, 3, 1. Okay, it's not looking good. Look, there's a 3 here. But I'll continue. 2, 2, 3, 2, 2. So what we have is we have 1, 2, 3, 4. We have 4 odd vertices. Which means it is not traversable, which also means the answer is no. So this completes the review. What I'm going to do is look at the puzzle now. Which word does not belong? Okay, so you may have figured this one out, and maybe you got a different word depending on your logic that you used. But the word that does not belong happens to be table. And the reason table doesn't belong is because it's the only word when read backwards that does not make a word. So look at this right here. Live, stab, drawer, stop, emit, loops, wolf, pets, pit, and diaper. So this completes the review for exam 3. Study hard, and I'll see you in the next video.